Vic sends his regrets. Just so everybody knows, if you haven't met Vic, or he was here for about a day and a half. Vic is part of the team. He actually is a management team that brought ductile to the U.S. More than 25 years ago. He would hate it if I said this, but he's really a UHPC historian. He is as aware of all the UHPC that has been done, throughout the U.S., Canada, and around the world as anyone else. He is a great resource if you're trying to do something for the first time. You think it's the first time ever. He's likely seen it, done it, tried it somewhere before, so ask him. He is a great resource. He has tried to share as much information with me as possible. That's why all of his hair left so that he could transport the information out of his head to mine. But Vic is a great resource. He's very, very high energy, even though he is in his...
He's older than you.
He's older than me. He runs, 25 kilometers a week. He has much higher energy than I am, but he's a good guy. He's a great resource, and he's very, very passionate about what he does. He has also left me some very detailed speaker notes, so I'll do my best to get through. His first slide speaker notes are, good morning. That's all he left me. But what Vic really was trying to cover here is the future of UHPC, what it means, where it's going, and how it's building on what's been done in the past. Vic really likes going with slapstick to start and draw interest. UHPC is the most sustainable material to build infrastructure. Larry just talked about how concrete's about 150 to 190 kg of CO2 per ton. You guys may have already heard me say this weekend. Steel is 1,850 kilograms of CO2 per ton, or if you convert it back to cubic yards, so we're playing in the same sandbox, it's about 450. So steel is 4 times more carbon intensive on a per unit volume than concrete, and yet concrete gets a really bad rap for being 8% of the total carbon and all the other bad things. It's all about changing the narrative, and it's about being efficient in how you use it. Our mission is to improve society's quality of life by building a more durable, resilient infrastructure with UHPC through the infrastructure that provides clean water, food, sanitation, and the movement of goods and the accommodation of people. This is the stuff that gets Vic up out of bed in the morning. He is very passionate. He believes it. He actually retired for the first time about 12 years ago, and he can't get away because he loves what he does. Our approach to this is by educating the community and applying a material like UHPC to reduce volumes and make sustainable contributions to help move the world towards a better, cleaner future. So what we're going to talk about is the global challenge, the sustainability of UHPC, some of the key material properties. I'll probably skip a little bit of that because we have really talked about it quite a bit this weekend. The opportunities, future markets, applications, some predictions, and then we'll conclude, and you can ask me questions or you can boo me off the stage because you've already heard me for an hour. The challenge. We have fixed resources on our planet, right? The population is growing, but resources are not. I believe Larry said it's about a 30-year cycle for timber to come back, so we can't rely on timber. We're running out of fossil fuels and things like that. Of course not in the next decade, but it's time we start thinking about it so we can keep pace with growing our infrastructure with the rate our population's growing. We're also seeing some more extreme weather. I mentioned that previously, the need for resiliency, fires, hurricanes, earthquakes, all of these things that can currently ruin or tear down structures. You're now at a complete restart. Everything that had been built there goes into a landfill and you have to build it over again. Resiliency can be very sustainable through reuse and continued, you're not re-embodying carbon. Additionally, we're up against the accelerated deterioration. If any of you look at the ASCE report card, I think we're something like 45% of our bridges are in need of repair or more. So the intention, and Larry also just mentioned this, is to get to a circular economy. The intention is that there's no waste. You can keep things in stride. The more you can reuse them, you're not re-embodying carbon, right? You're being more efficient, and that's through the repurposing. It's through increased resiliency. It's through lower embodied energy up front by thinner materials, et cetera, and it's through social change. Larry also just talked a lot about making intentional decisions to reduce this carbon. It's not going to happen automatically. The net zero challenges that have been put forth and that pressure we've been put under, it doesn't happen accidentally. It can't happen 100% at the cement level. It's got to be an entire decision to change through the process. So, just to cover briefly, you see on this graph all the way to the left, HPC. This shows you rough thicknesses of high performance concretes based on the lifespan that you want to have. You can see here that the intention of UHPC is to be significantly thinner to achieve those lifespans. So now you're reducing carbon up front by using less material, and you're reducing carbon by lasting longer. If you had a material that lasted 25 years to first maintenance and 35 years, let's say, to end of life, and you can use a UHPC that is, let's just say, 75 years of life, you're now at a factor of 2. You can cut your carbon in half in the life cycle of that structure. You'll see on the right here, this is a study that was done in Treat Island, Maine. They put a bunch of UHPC, traditional concrete, some other products in the water in Maine that's subject to a few hundred freeze-thaw cycles a year, very brackish waters, tidal action, etc. After 1 year, the regular concrete, when they came back to look at it, was gravel. After 20 years, there's no noticeable corrosion that's deteriorated the UHPC. So that's really the intention we're after here. We want to have a material that can get up on the building, stay there, and you don't need to come back and touch it. How do we do that is, the ductility of UHPC. I showed a couple photos earlier. You can see here a bridge girder that has been it's been subject to incredible deformation. That's what this material can do. It can also provide additional capacity post-crack and other unique things like that. These are the levers that we can use in design before it ever gets to your plant, or when you're trying to bring an opportunity to you. These are the levers that you apply to maximize that sustainable choice. What is UHPC? I'm going to entirely skip this slide because if I say it one more time, there's probably going to be a few yawns and maybe some shut eyelids. But there's some key important properties of UHPC. We already talked about, flexure really is the one that's going to matter the most to the people in this room. Beyond that, permeability and water still matters to you. Abrasion matters. There are several things about UHPC that the ultra comes into place. So the elastic modulus, the stiffness of this material relative to regular concrete. Direct tensile strength, if you have to get into something of that sort, it's a whole different can of worms, so pick up the phone and call. I won't cover that now. I don't want to confuse the matters. So one of the things to understand about where the applications are is to talk about the casting methods, what's already been done. We've talked about the material being unique. It does not behave the same as regular concrete. It's a non-Newtonian fluid. If you don't know what that means, basically the harder you try to move it, it's not going to respond like a regular concrete. It has several different things about it that are unique. The development of an elephant skin, the self-consolidating nature, the increased hydrostatic pressure. All of these things are unique, and thus over the years, to accomplish different goals, we've come up with different casting methods. So all the way to the right, you'll see a traditional, this is what we just saw yesterday. You discharge material into a hopper, fly your hopper to wherever you want to go, and you pour it. It'll self-consolidate, it'll take the shape that you want as long as it's flat on the top. If you want to make a shape that isn't flat on the top, wait a minute and I'll show you how to do that too. The next one, it has been spin casted. That is where I will punt. If you have a question on spin casting, I can give you Vic's number, but that is not one that I personally have experienced. The intention here is to show you what has been done, what can be done, and if you want to do it, you're not the first one to learn from other people's mistake. Injection casting. This is where you use either pumps or hydrostatic pressure to fill a mold from the bottom and push all the air out, and then you can take whatever shape you want to take. Of course, spraying, there's a lot of GFRC producers in this room. You can also spray UHPC. It will likely require modification to your equipment, at least the nozzle, but this is a picture of some spraying that we're currently doing in China. Not likely going to seem anything profound to you. If you spray GFRC, the process is, it's very similar. There are also other things you can do like extrusion, stamping, etc. But just to show you that it's proof, seeing is believing. You can actually spray UHPC even if it seems like it's too thick.
The spraying, we kind of talked about having that continuous fiber matrix. Does spraying it affect that?
That depends on what you're using to pump it and spray it, but you certainly can get a fiber matrix when you spray UHPC. This is a fiber reinforced UHPC. It just basically is about what you're using. The type of pump matters. I believe GFRC typically injects fiber or cuts it at the nozzle. You could do that with an acrylic fiber and UHPC just like you could with GFRC. So I guess I don't like giving the answer, it depends, but it depends. I mentioned, you pour something vertical and you want it to take a shape that isn't flat, it can be done. Well, the way you do that is called displacement casting. So this is a waffle deck panel, but basically we poured something, we did some math and said, all right, we have to pour it 6 inches thick and then we'll push the form in and it will take the 8.5-inch profile and it will have these voids in the back so that we have the stiffness and strength of an 8.5-inch profile, and we save the material so that in between those ribs, this is 2.5 inches thick, but it's designed for heavy vehicle traffic. Tim mentioned, and you saw that they've poured some things with ribs. You can make the panels thin, and then you can use a process like this to have a rib to maximize your thickness maximize your strength, or even to have an easier return to the building for connection, kind of tying on to a question Nick had previously. And then here's just another video of some material pouring. We all got to see this yesterday. This is a dark gray material. Again, it's intended for infrastructure. There's no need for color match, etc. But it shows you what you can expect. This, Vic calls it semi-closed rotational. I wouldn't say that's like a coined or trademark name, but basically this was an effluent trough. They had this, you can see the shape in the top left. There's a depression throughout the full length of the top. The easiest way to pour this was upside down. But as Roy and Tim mentioned yesterday, when you have UHPC, particularly the more mass you have, the more heat it can generate and the more it can shrink. If you try to restrain that too much, even with the fibers, you can crack this material if you don't release the restraint. So something like this, they poured it upside down, they got the material in the form, you use what's called the Vicat needle, basically, just check what your set time is on the concrete, and then at the right time, they pick up on an eccentric cam to have the whole form rotate back up. They could then release the form restraint at the top. Then it's also in the orientation where they wanted to ship it and use it. Now this is a very busy slide, but the intention here is to show where the future of UHPC is. And the answer is from down in your foundations to as far as you're going to build up in the sky. I also mentioned before that it's not one size fits all. Everything in the world is not going to be made out of UHPC. So the intention of this is not to think that no longer will we use regular concrete. It's to show you that there can be a value application no matter whether it's buried in the ground or it's 1,000 feet off the ground. Some of the things you'll see up here in the top right, there are culverts. We're seeing a lot of need for culverts and storage tanks and things that are high abrasion from moving water, high chemical from different plants and settlements. Those are great applications for UHPC. We've seen columns, foundations, connections. Obviously, you'll see several high-rise buildings here. You saw pictures on my presentation of a building that was 7,000 tons of UHPC. We have used it for foundations of wind turbines, even in the middle of the ocean. You can use this underwater. It is great in that application. Your standard house, right? If you have a house in California that's in the realm of fire country, this is resilient and fire resistant more than wood and other alternatives. So what is UHPC bringing to the equation? Why is the future from the foundation to the ceiling? It's because it brings a freedom of expression to build infrastructure. You combine beauty and strength. You know, Gary talked about making a railing that is now attached to a structural piece of beautiful concrete compared to having to alter that system to go down to your structural slab. On the left here is the Lucille Towers. That's the project I've continued to refer to. It's a couple of high-rise buildings that were built in the Middle East, all with UHPC facade and window returns. You have an example here of some perforated screens in Orlando. Here's some of the other complex perforations that you can do that you couldn't do with traditional concrete. You know, you can't make reinforcement follow those curves and bends. You need a three-dimensional dispersion of fiber to accomplish the strength to do something like that. Here's the picture of the canopies again. You can see some cornice and some other perforations. The intention is that you have freedom to do basically anything that you want to do. Anything you're crazy enough to bite off, you can probably do it. It all will come back to the value chain and how much time and effort you want to put into making it happen. Surface finishes. We've talked a lot about how much this can mirror a surface. That's generally said in a positive light, but as Roy alluded to, it can also be a negative. So if you're going to get into this, I will also add that you should pay attention. Your form oil, the product you use matters, the way you apply it matters, etc. But you can come up with beautiful and detailed finishes like this, all the way down to, if you really felt inclined, to make a record with UHPC. You know, it's an artistic expression as well. You can see here, I mean, this could be done out of traditional materials. It's not to say that this could not be accomplished with UHPC. It's more about, can UHPC bring a value to whatever it is you're trying to do. Furnishings. We have seen a lot of unique shapes with lawn furniture and, you know, seats, etc. It all depends on how much your architect wants to bring what they're doing to life. Balconies, bathroom pods. I'll talk a little more about what the volumetric market is going to look like, but these are things that don't jump out as, well, why would I think about that? Well, because of what UHPC could do, you can make an entire balcony, have it thin enough that you could ship it out and achieve that strength and that beauty. This is an example of a piece, again, that was poured in China with Sientech material. This was a mock-up that they completed. They hung off the building. They wanted to see how it would react to the weather and how it would look with the metallic and the glass of the building. Here's another example of a panel. I talked about it before, but you want to make sure you level the expectation with your architect. So the future of UHPC is going to be rather broad, but right now it is not quite so broad. Mock-ups are a great way to get an architect to understand what they're buying. A lot of architects do not yet know and understand what UHPC is, what a UHPC finish looks like. Here's another option that I think many of you don't do currently, an insulated sandwich panel, because of how thick and heavy they can be. UHPC brings the opportunity to make something like an insulated sandwich panel light enough that you could do it with your cranes, and you can also bring the craftsmanship and the beauty to something like that. A lot of this market right now is done more on a PCI architectural finishing type criteria, which certainly does not meet the snuff of some of the beauty that you guys can produce out of your plants. Basically, you have one layer of reinforcement. You pour as thin as 20 millimeters. You have your standard insulation in between shear connectors, and then you pour your back width. But instead of it maybe being somewhere between 8 and 12 inches entire composite for regular concrete. You could be down to 4.
What are you connecting?
To the building or in between?
Between the insulation?
There are 2 companies I'm aware of right now that use shear connectors, but they have special connectors that they've developed to be in the thin panels of UHPC. So if this is something that you're interested in, we're doing a lot of research right now on it at University of Calgary. We do have some information on details, connections, etc. Happy to share. You'll see here modular construction. This is something that is very big right now around the world. Canada has a housing shortage of almost 500,000 habitable homes versus their current population, which is growing as people are coming to Canada. How do we build cheap, fast, resilient structures and not double our general contracting resources? We have to be able to do this with the builders and resources that we currently have. There's 2 approaches. You can go volumetric, which is pre-connected, you deliver it, you drop it, and you stack on it and you keep moving, or you can go with the IKEA approach. Build it in a lot of segments, tilt it up, connect it in place. What we've seen is that the requirements, the labor, et cetera, on site, there just isn't enough contracting labor to go around to take the IKEA approach that's a little bit cheaper from precast. You can't get it built, at least not at the rate that we need housing. UHPC is what you would consider a breakthrough or an innovative product. And as all products in that category go, it's kind of in an S-curve development. Think about a cell phone in 1996. The really, really rich people had a cell phone and they could drive around and make a call from their car. Nobody else had it, but everybody thought it was cool and wanted it. Right now, if I asked everyone to raise their hands who doesn't have a cell phone in the room, everybody has a cell phone. So that market slowly scaled up, the interest caught, and then it was basically straight vertical until you saturate, and now that market's mature. Everyone's going to keep buying a cell phone every year or 2, or if you're as bad as I am and you break it in 6 months, maybe a little faster. But the intention is that curve is proven in economy, capitalistic society for a long time. We're right about at the base of that vertical. Every convention you go to, people are talking about it. Owners want it. Producers, obviously 88 people here are interested in paying attention and learning how to be a part of this curve. This is where we see it. The exact length of the scale-up curve, we don't know, right? It's a prediction just like anything else, but it's very clear that the attention and the energy is here. The need for solutions is here, and thus we believe we're pretty close to that spot where this is about to jump. And so now I'll conclude. You remember back to one of the first slides. We live on a planet with fixed resources, growing population, and increasingly damaging weather and other things. We need to find a way to keep up with that from an infrastructure and cladding, everything from our buildings to our roads to what's down below the earth. The superior strength and durability properties of UHPC is what makes it the most sustainable product to build infrastructure with. That does not mean that 1 cubic yard of UHPC in a 1 by 1 by 1 yard block is better than a 1 by 1 by 1 yard block of concrete. It's all about the application and how you make the most value of that cubic yard of material. It's a breakthrough technology, which means we're in that S-curve. Right now, we're not doing 2 million cubic yards of it in the US. We are working towards that, though. As I mentioned, the interest is there, and it is not something that can be figured out overnight. So the time is now to start paying attention and try and grab on and catch that vertical rise up through the market. And by 2040, the global demand for UHPC is expected to approach $100 billion for $1 trillion worth of construction on those projects. That gives you, and that number is not just something we're projecting. If you look around at people who have projected the market, it is expected to grow exponentially. Does anybody have any questions? I'm the last thing keeping you from lunch, so I'll be quiet and I can move. Thank you.